A really good afternoon to my supervisor, Professor Lu, and my examiner, Dr. Loke. My name is Joshan, and in this video, I'll be sharing about my final year project, which is about training deep neural network models for accurate recognition of text in scenes. But first, a quick overview of what I'll be going through, beginning with a quick introduction to the topic at hand, followed by establishing the project objectives. I'll then briefly cover the network architecture of study that I used to build the model before jumping into the experiments and outcomes. A live scene text recognition program was also built as part of this project, along with a trial of serving this text recognition service behind an API, both of which will be demonstrated in this video as well. And finally, I'll wrap up the video by covering the current limitations, future improvements, and possible extensions of the programs. Scene text recognition, as both Professor Lu and Dr. Loke are very familiar with, has been a well-established research area and certainly not a trivial task, due to a variety of factors that can influence the accuracy of recognizing text in images. These factors, for example, include, but are not limited to, environment lighting and complexity, image quality such as degradation from blurring and pixelation, and the physical appearance of the text itself, such as size, font, color, and more. In fact, text recognition is just one out of two steps from the entire text transcribing process, the other step being text detection. In the past, text recognition methods mainly extract low or mid-level handcrafted image features. They generally comprise of three steps, namely image pre-processing, character segmentation, and character recognition. Much of the efforts back then were focused on the designing of the image features in order to segment the characters as accurately as possible, which was considered to be the more difficult task out of the three. Some examples of these past text recognition methods include character segments-based algorithms and label embedding, which performs a matching between strings and images based on a distance metric. But this is where deep neural networks come into the picture, in which they avoid the character segmentation step by automating the feature learning process, thus removing the need to create and test huge volumes of handcrafted features. Two major techniques of avoiding the segmentation step include the connectionist temporal classification, which computes a conditional probability of the label sequence based on a set of per-frame predictions, and the attention mechanism, which computes an attention weight to decide the next sequence while decoding a target sequence. As such, this project provides an opportunity for me to explore deep neural network architectures for scene text recognition, and the following are my two main objectives. Firstly is to understand such architectures along with the training process by emulating the results of a reference paper, specifically the Convolutional Recurrent Neural Network, or CRNN for short. A CRNN model will thus be trained, and its hyperparameters will be experimentally obtained to understand their impacts on the model performance. Secondly, a live text recognition program will be created to demonstrate the trained model's efficiency in a real-time scenario. The CRNN, as its name suggests, is a combination of a convolutional neural network, or CNN, and a recurrent neural network, or RNN. It conducts image-based sequence recognition through three main segments, namely the convolutional layer, which extracts a sequential feature representation from an input image, the recurrent layer, which predicts the label distribution for each frame, and finally the transcription layer, which translates per-frame predictions into a final label sequence. Within the convolutional layer, images are first rescaled to the same height of 32 pixels, and then feature maps are generated via the convolutional and max pooling layers, much like in a typical CNN model. Thereafter, a sequence of feature vectors is created from the feature maps by essentially chopping them up into single pixel width columns from left to right, and these sequence of feature vectors would then be passed on to the recurrent layers of the network. The recurrent layer consists of a deep bidirectional RNN with long short-term memory cells, or LSTM, and it predicts the label distribution for each frame xt in the feature sequence. LSTM cells are used instead of standard RNN cells, as they are able to capture long-range dependencies which often occur in image-based sequences. While LSTMs are unidirectional and only uses past context, in image-based sequences, however, context from both directions can be useful and complementary to each other, much like how if the alphabet W was split into multiple frames. Hence the use of a bidirectional LSTM by stacking two LSTMs on top of each other, both going in different directions as shown here. Finally, in the transcription layer, the per-frame predictions from the recurrent layer are then converted into a label sequence L, based on a conditional probability defined in the connectionist temporal classification. L is a set containing English characters and hyphens which represent blank spaces. A sequence-to-sequence mapping function is then mapped onto sequence L by firstly removing repeated labels and then removing blank spaces, giving us the final predicted text as output. So with this basic understanding of how the CRNN works, we'll move on to the experimentation details. Training was entirely conducted on a paid platform called Paperspace Gradient, which provides a GPU-enabled Jupyter Notebook environment. The table here gives an overview of the hardware setup Paperspace provides under its GPU Plus plan, which I used. Software-wise, Python of version 3.6.7 was used with PyTorch as the primary machine learning library. The following here are the datasets used in the project. The CRNN was trained with the MJ-Synth dataset comprising of about 9 million synthetic text images. Fine-tuning was also attempted after training using the CocoaText dataset. For the testing of the model's performance, we'll be measuring the model's accuracy with two benchmark datasets, namely the ICDAR 2013 and the IIIT 5K words datasets. These datasets contain 1015 and 3000 images respectively. However, the author of the CRNN paper highlighted about some constraints in the images used for testing in his GitHub repository, specifically that the images should only contain alphanumeric characters and have at least 3 characters. Unfortunately, there were no filtered dataset made publicly available by the author based on these restrictions, and thus I manually filtered the ICDAR 2013 dataset to 857 images, which was the quantity mentioned by the author after his filtering. There was also another thread about filtering for the IIIT 5K words dataset, but it had no replies from the author. Nonetheless, I also manually filtered the IIIT 5K words dataset based on these constraints and used both the filtered and unfiltered IIIT 5K words dataset for testing. These are therefore the 3 datasets with their corresponding volume of data that I used to measure the performance of the final model. Moving on to the experiment methodology, the experiments conducted primarily revolve around the tweaking of 4 hyperparameters, namely the type of optimizer, learning rate, batch size, and number of epochs, to seek the best configurations that will contribute to an optimal model performance. The experimental values for each parameter are tabulated here as well. For the number of epochs, however, I decided on implementing early stopping in the training instead of experimenting over arbitrary values to have things more deterministic and less naive, something which was not covered in the paper. As such, a total of 3 experiments will be conducted in this order, and these will be the controlled variables and their values for each experiment. The best option obtained from each experiment are also applied subsequently. Experiments will be conducted with 50,000 training images from the MJ-Synth dataset and over 10 epochs to speed the training process during these experiments. But the final model will be trained over the entire 9 million images with the early stopping mechanism. We also split the image set by a ratio of 8:2 into our training and validation datasets respectively. Key performance indicators that I'm using to measure the model performance include speed of convergence, training and validation loss, and model accuracy, all of which will be plotted against the number of epochs. First off, we have the results for the optimizer type. The differences in performance across the optimizer types are pretty distinct, with the worst performing being RMS Prop, and the best performing being the Abdon optimizer, all of which being based on the speed of convergence and the final loss values and accuracies at the end of the 10th epoch. Hence, the Adam optimizer was decided to be the best out of the 3, which actually differs from the paper in which they published that they decided on Eta Delta for its faster speed of convergence. Next are the results for the learning rate experiments. We can observe right off the bat that the learning rate of 0.01 is too high since the model isn't learning at all. So we'll compare between the other 2 values. Again, it's pretty clear that 0.001 outperforms 0.0001 in terms of speed of convergence and accuracy. There's notably less noise as well, and hence we'll take 0.001 as the optimal value. And finally, here are the results for the batch size experiments. We can generally observe from the 3 plots that the speed of convergence is fastest for batch size of 64. The final validation loss appears to be more or less similar across the 3 experimental values. But for validation accuracy, the batch size of 64 reflects the fastest convergence as well as the highest accuracy. As such, we'll take 64 as the optimal value. With this, we have the Adam optimizer, a learning rate of 0.001, and a batch size of 64 as our optimum parameters. A CRNN model was then trained over the entire MJ-Synth dataset for a total of 30 hours and 38 minutes on Paperspace's GPU. The plot on the left here shows the training and validation loss comparison, while the plot on the right shows the model accuracy as it trains. The red dashed line indicates when the early stopping began counting, and we can see that the validation loss was starting to increase from when the early stopping started counting, hence showing that it prevented overfitting. The final validation accuracy marked by the early stopping was at 90.67%. Final accuracies against benchmark datasets are also as follows, with a slight improvement of 1.05% against ICDA 2013 as compared to published results, and a very slight improvement for IIIT 5K words of 0.2%. I also tried to fine-tune a model in which I initially planned to use the training images from the ICDA 2013 dataset. However, it only comprised of 848 images, and this resulted in significant degradation of the model's performance after attempting to fine-tune. Hence, I decided to look for an alternative dataset to fine-tune with, something of much greater volume, and decided on the CocoText cropped images dataset, which consisted of 41K images. This, however, gave mixed results as well, as shown here. Fine-tuning with the CocoText dataset seemed to favor the IIIT 5K words dataset, with an improvement of 1.9% in terms of accuracy from the pre-fine-tuned model based on the unfiltered dataset. But the accuracy against ICDA 2013 dropped by 1.64%, which fell below the published accuracy. And with this, that wraps up the model building process. So we have a model that can spit out predictions of text given a cropped scene text image. But what can we do with it? Companies like Google have built apps that use a scene text recognition technology with beautiful results, such as Google Translate's live translation feature. So I decided to give it a shot by making something similar and simpler with a live text recognition program. The program is able to detect text through either static input images as well as a camera feed, and is able to maintain about 20 frames per second, although it does degrade to about 10 frames per second if there are high density of text in the camera frame. Furthermore, the program can also arrange the detected text in static images in the order which they are meant to be read from the image, and I will give a quick demonstration on all of this in a bit. Each input image or camera frame basically goes through this pipeline. Firstly, text regions are extracted via a pre-trained east text detector, and each text region goes through some pre-processing to align them horizontally before being passed into the trained CRNN text recognizer. Finally, with the predicted text, we also arrange them in the order which they are meant to be read, and the output of the program is just the arranged text, along with an output image with text regions marked by bounding boxes and their transcribed text placed above the boxes. I'll cover more on how I do the pre-processing on the extracted text regions via angular correction as mentioned, and how I arrange the detected text in order further into the video. But first, here's a quick demonstration on the program. For the demonstration of the live text recognition program, I'll just be showcasing the recognition of text on various household objects that I have at home, with increasing difficulty in terms of text density and text appearance variability. The program definitely works best when the contrast between the text and its background are at the greatest, but is still fairly stable otherwise. I use single text examples such as the first two objects as a baseline to the program's correctness, and eventually move on to objects with multiple texts. Here, you can also notice that the program begins to slow down a little when there's a high density of text on the object. And finally, the program is also able to function well under non-standard font families, such as in this object. Now, I'll be demonstrating the program again using static images as input. Now, all of the images used here are from the Street View text dataset. And we can observe here not just that the transcriptions of the text are correct, but also the sentence formatter seems to be working fine as well. There are nonetheless images like here, which are transcribed incorrectly either because of the text detector not extracting the text region properly, or the text recognizer not transcribing the text accurately. Here is another example where the text detector did not manage to extract this particular word, but nonetheless the sentence formatter seems to be working fine. So given a scene image, The text detection model does not consider any form of ordering when detecting text regions, which I personally felt that there will be more tangible use if the program can also print out the text in the order which they are meant to be read based on the picture. As such, what I did was to use the bottom two vertices of a text's bounding box, form a linear equation with them, and find its y-intercept with the left edge of the image. Thereafter, I'll basically deduce that two texts are on the same line if the difference in their y-intercepts are within a specified threshold. So for example, in this picture, the words please and take belong to one line, and the words nothing and but belong to another line. This method takes into consideration the orientation of the text too, and is shown to be robust as with this example here, in which the texts were ordered correctly. Here is also another example. I try to use images with higher density of text to show the correctness of these features, which I call the sentence formatter. However, we may also have a situation in which there are multiple contexts of text, such as here, in which based on human observation, we can infer that there are three groups of text here, although some of them are wrongly detected. Going by the earlier algorithm, the words on the far left and right ends of the images will therefore be considered to be lying on the same row, which is incorrect, since that wouldn't be how we would read the words in the image. This is where we bring in an X threshold to determine if words on the same row are meant to be in the same context, by comparing the X value of the bottom right vertex of the left text bounding box and the bottom left vertex of the right text's bounding box. If their difference is outside of the threshold, two words will then be considered to be of two different contexts and hence will not be grouped into the same row. And just to show another example for words on the same row with the consideration of the X threshold value, if the difference is within the threshold, the words will be treated as on the same row. So this is where the sentence formatter logic is currently at. We can also perhaps perform clustering of detected text such that Mount Vernon Hotel Cafeteria is taken as one group, simply by doing one more comparison of the Y values of the corners of each text's bounding box, but this is yet to be implemented. Now that I've got a live text recognition program working, I was actually thinking of how I could port this feature over onto mobile or web applications, where it can actually be used by users, rather than running the program on my machine's command line. And that's when I realized a certain difficulty in doing so, the compatibility between languages. Most machine learning models are written in languages which differ from those that are used to write applications. This project, for example, was mainly written in Python, but web and mobile applications use other languages such as JavaScript, Java, or Swift, just to name a few. As such, deploying a user function that depends on a model most of the time requires the use of a plugin interface. Yet again, plugins are not always available depending on what framework was used to build the application, not to mention the possibility of added complexity. Thus, I tried building an API server in hopes to improve the accessibility of the text recognition feature, such that applications will just have to call the endpoint of the server rather than having the function integrated into the application directly. This may also assist platforms with limited computation capabilities as the computation is offloaded to the server instead. The RESTful API server is written in Python and built using Flask. To demonstrate the functionality of the server, I've also built a simple web and mobile application, the former written in JavaScript using the Vue framework and the latter written in Dart using the Flutter framework. I'll now demonstrate briefly the Python API server along with the web and mobile applications, starting with the web application first. So as mentioned, the API server was built using Flask and the web application was built using Vue. So we'll now proceed on to localhost 8080. And this is the web application. So a handful of features here on the web application. We can toggle between the static images or a live camera feed, but for static images, we just have to upload an image. Give it a short time to compute and we'll be able to see the output from the server as such along with the sentence formatter at work. So users can also click on the output image to expand it and view it in greater detail. For the live recognition feature on the web application, it functions just the same as the program, just with a proper UI this time, showing the original camera feed on the left and the computed frames on the right, along with the detected text arranged as below. Now, the API server and web application are both running on the same machine and hence communicates via localhost. For the mobile application, however, we'll use a program called ngrok, which allows local servers to be exposed over a secure tunnel via a public URL, and this can be done as such. And here, our mobile application can access my machine's API server through this URL. So here is the mobile application. As mentioned, the mobile application was built using the Flutter framework, and it has two main functions just like the web application, mainly static images and live camera feed, but for now only the static images work. So we'll first establish our communication with the API server by keying in the ngrok ID. And once communication has been established, we'll get a success notification here. From here, we can just select an image, wait for it to compute on the server side, and our server will reply with the image here. And users can also zoom into the image to view the image in greater detail. Now, the text recognition program is definitely imperfect. By computing an input through a pipeline, errors will be propagated to each subsequent step, which affects the accuracy and, more importantly, the correctness of the final output. For current limitations, firstly is with regards to the text detection model that I used. The East model doesn't seem to handle geometrically long text or sparse text very well, as evident here, where it detected the word restaurant in 3 separate chunks. There are also instances where the East detector marks out a text region, but the bounding box does not cover the entire text region as shown here, potentially stripping away important information. Initially, I thought of a solution to extract the text region by using the maximum boundaries of the 4 corner vertices of the bounding box, as shown here. But this leaves us with white spaces, which possibly affects the performance of the CRNN model's prediction, particularly when words are oriented above 25 degrees from the horizontal. This image here might still be fine, but the following image here exemplifies the inaccuracy in terms of text prediction. This is where my angular correction comes in which I essentially try to rotate the text region such that the text is as horizontal as possible before feeding it into the CRNN. For each detected region of text, I first find the gradient m and angle of orientation theta of the word using the bottom 2 vertices of its bounding box via the following equations. Depending if the gradient m is positive or negative, it will determine the rotation direction to be clockwise or counterclockwise respectively. Thereafter, we first rotate the entire image by angle theta, then rotate the 4 points of the bounding box with respect to the center of the rotated image by an affine transformation. This gives us a horizontally aligned detected text region as such with minimum white space, and we finally extract the detected text region with the maximum boundaries of the bounding box again as demarcated by the red dashed lines, then feed it into the CRNN text recognizer for prediction. There are also some other limitations such as hardware limitations, for example the camera on my laptop being able to only support up to 30 frames per second and the lack of GPU for faster model inference. As for future improvements to this program, as mentioned, clustering of text into groups is possible, such that for example here, the program will take Brown's Arcade as one group and Hair Salon located inside as another. Not to mention that it will also be best to train my own text detection model, which not necessarily has to be an East model, to have greater clarity on the performance and accuracy. It is, however, important that the model is efficient in terms of inference speed. We could also possibly train a new CRNN model to recognize non-alphanumeric characters and also discern between upper or lowercase characters, both of which are commonly present in scene images and hence potentially very useful. Furthermore, we could even leverage on the generalizability of the CRNN model, as mentioned in the paper, to train the CRNN on another set of language, although understandably, each language brings about a whole new set of rules and hence difficulty. With this, as I reach to the end of the video, I'd like to just quickly recap about what were achieved from this project. So firstly, a CRNN model was built in which its hyperparameters were experimentally obtained, a small note being that I used a different optimizer than what was mentioned in the paper. Next, I also added 2 enhancements on top of the published paper, namely early stopping and fine-tuning. The latter, however, resulted in mixed results, where the model favored the IIIT 5K dataset over the ICDA 2013. Nonetheless, the final model emulated the published state-of-the-art results successfully with a small improvement in accuracy against the ICDA 2013 dataset. And finally, a live text recognition program was built, along with a feature to display the detected text in the order which they are meant to be read. And the trial of serving the text recognition feature behind an API endpoint was conducted, which proved quite fruitful. And with that, thank you so much for your kind attention to the end of this video. If there is an interest in the live text recognition program that I've built, I've pushed it up onto a public GitHub repository and the link is as shown here.